Hi students, today we are going to discuss adiabatic demagnetization, and it is one method of to producing a low temperature. So here adiabatic demagnetization is nothing but the experimental arrangement to produce a low temperature by adiabatic demagnetization is called as adiabatic demagnetization. We can mention. So it is the experimental arrangement to produce low temperature. The experimental arrangement to produce a low temperature by adiabatic demagnetization. So adiabatic demagnetization, in the sense, it's an experimental arrangement to produce a low temperature, that we can call it as adiabatic demagnetization. So here we are going to observe a diagram for adiabatic demagnetization process, and here we are using two flasks, and the paramagnetic salt is taken in this experimental arrangement, and this paramagnetic salt which is taken at the center of this arrangement, that we can call it as vessel. Let us consider this one as a vessel, a paramagnetic salt, in the sense gadolinium sulfate, that is taken in a vessel, and it is surrounded by the liquid helium. So we are consider this one is a liquid helium in a flask, and this liquid helium is surrounded by the liquid hydrogen, and the whole instrument is placed in between north and south pole of a powerful electromagnet, and this represents adiabatic experimental arrangement of adiabatic demagnetization. Here we are going to observe the explanation of this adiabatic demagnetization. A gadolinium sulfate is suspended in a vessel which is surrounded by a liquid helium, and this liquid helium is surrounded by a liquid hydrogen using the flasks, and the entire arrangement is placed in between north and south pole of powerful electromagnet. So now what happens if that electromagnet is switched on? Electromagnet is switched on. So the temperature of that paramagnetic salt increases. What we take on the paramagnetic salts in a vessel is increases when the magnetic field is on. If the magnetic field is on, the temperature of the paramagnetic salt rises, but that heat is conducted by the helium gas. When the temperature of the paramagnetic salt rises, the heat is conducted by the liquid helium gas or helium gas, so that the temperature of the salt falls to the original temperature. So in a helium bath, already we are discussing that. So this adiabatic demagnetization we are discussing to produce a low temperature. When by considering this experimental arrangement, it produces a low temperature, and even we have to produce a low temperature, in a sense less than this temperature. So the temperature of the paramagnetic salt rises, but the heat is conducted by the helium gas, so that the temperature of the salt falls to the original temperature, initial temperature we are going to get. Now we have to produce less temperature than this original temperature. Here the conduction takes place, in the sense the exchange of a helium gas in A is pulled out, so that the salt is thermally isolated. Here they are explaining adiabatic demagnetization. Adiabatic demagnetization, in the sense heat neither enters the system nor leaves from the system. Therefore the produced heat is diffused by the diffusion pump from here. And this about experimental arrangement when the magnetic field is switched on. Now we have to produce temperature less than this original temperature. Therefore, if we switch off this magnetic field, now the magnetic field is switched off, the salt instantaneously gets demagnetized. If that salt gets demagnetized adiabatically, and the temperature is falls less than that original temperature. Now to measure that low temperatures, we have to use magnetic thermometers. So by using a susceptibility dimension, according to that, the Curie's law. So here in this case, we are going to get the low temperature when we switch off the magnetic field, electromagnetic field. If we switch off, the salt gets demagnetized. At the time a low temperature is produced. To measure that low temperature, the magnetic thermometers are used. Here to measure the temperature of salt, susceptibility is measured, and even we have to measure the susceptibility with the help of magnetic thermometers. According to that, so Curie's law, we are going to observe an expression for Curie's law. Psi of T is equal to constant. So we discussed it in a PU section, that is a Curie's law. Psi T is equal to constant. Here the psi that represents the susceptibility. Here we can call it as psi. Yes, psi, right? Susceptibility. Now if we simplify this one, we are going to get a psi 1 T1. We can also represent psi 2 T2 here. Therefore this can be written as psi 1 divided by psi 2, which is equal to T2 divided by T1. So psi 1 divided by psi 2 is equal to T2 divided by T1. Therefore T2 can be written as T2 is equal to psi 1 divided by psi 2 into T1. Let us consider this one as an equation number 1. From first law of thermodynamics, dq is equal to du plus of dw. This can also written as dq is equal to du plus of p into dv. Now from second law of thermodynamics, dq can be written as t into ds is equal to du plus of p into dv. Let us consider this one as an equation number 2. When the paramagnetic salt is placed in a magnetic field, we discussed by an experimental arrangement, when paramagnetic salt is placed in a magnetic field, and the intensity of magnetization decreases. Magnetization decreases by di. Therefore, so the work done on the salt, that can be represented by B into di. Therefore equation number 2 becomes, equation 2 can be written as, equation 2 becomes, so TdS is equal to du plus of P into dV minus of B into di. We are going to get here there is a decrease in that intensity of magnetization takes place. Therefore we are consider the negative sign here, and this represents a magnetic field, and this represents decrease in the magnetization, intensity of magnetization, that is di. So let us consider this one as an equation number 3. Now the demagnetization is carried at a constant pressure. The demagnetization is carried out at a constant pressure. So the demagnetization is carried at a constant pressure, in the sense the change in a volume is 0, in the sense there is no change in a volume takes place. If there is no change in a volume takes place, therefore equation 3 can be written as TdS is equal to du minus of B into di. So let us consider this one as equation number 4. So TdS is equal to du plus of P into dV minus of B into di. Here, if at constant temperature the demagnetization carried out, therefore the change in a volume which is equal to 0. There is no change in a volume at a constant pressure. Therefore TdS is equal to du minus of B into dV we are going to get. So comparing equation 2, and this one is an equation number 2 and equation 4. If we comparing these two equations, here we are going to observe P is replaced or corresponds to that replaced by minus B, and I is replaced by V. So here V is replaced by I and P is replaced by minus B. Therefore comparing equation 2 and 4. Comparing equation 2 and 4. So it gives that minus B corresponds to P and I corresponds to V, right? Now according to Maxwell's thermodynamic relations. So we know that dou T divided by dou P of S entropy, dou V divided by dou S of P. We know that minus B is correspond to or changed by P, and I that can be replaced by V. Is that right? Therefore we are going to get minus of dou T divided by dou B of S, which is equal to, in the place of V we are substituting I, dou I divided by dou S of B. So here the magnetic field is there, therefore we took a B here. Now this can be replaced by dou I divided by dou T of B into dou T divided by dou S. So we are multiplied by dou T and divided by dou T, and the same concept we are going to get if these two gets cancelled. So now this can be written as dou T divided by dou B of S is equal to minus of dou I divided by dou T of B in numerator and dou S divided by dou T of B in denominator we are going to get. Let us consider this one as an equation number 5. We know according to Newton's second law of thermodynamics, we know dq is equal to T into ds. Now this can be written as dou S is equal to dou Q divided by T. Dou S is equal to dou Q divided by T. Now dou S divided by dou T is equal to 1 by T into dou Q divided by dou T of B we are going to get. Now this can be written as dou S divided by dou T is equal to, so dou Q divided by dou T of P, that can be represented by M CB divided by T. Let us consider this one as equation number 6, where M is the mass of the specimen or mass of the salt we are going to get, paramagnetic salt, mass of a specimen, and Cb is the specific heat at a constant magnetic flux density. Specific is the magnetic flux density. Now equation 5 becomes, now equation 5 can be written as dou T divided by dou B of S entropy, which is equal to minus of dou I divided by dou T of B divided by, in the place of dou S divided by dou T of B, so we have to consider dou S divided by dou P of B is equal to M CB divided by T. If we simplify this one, dou T divided by dou B of S is equal to minus of T divided by M into CB, so dou I divided by dou T of B we are going to get. Now this can be written as dou T is equal to minus of T divided by M CB into dou I divided by dou T of B into dou B. Let us consider this one as an equation number 7. Just we cross multiplied this one. Equation 7, this equation 7 represents the fall in temperature of a specimen, fall in temperature of a specimen due to adiabatic demagnetization, and this is an expression for fall in temperature. If we move further, this can also written as by integrating on both sides, we are going to get by integrating so dou T, left hand side dou T we are going to observe, therefore initial temperature to a final temperature integration, which is equal to minus of integration of Bi to Bf T divided by M into Cb dou I divided by dou T of B into dou B. So this can be written as Tf minus of Ti, final temperature minus of initial temperature, which is equal to minus of Bi to Bf T divided by M into Cb, differentiation of these two terms that can be represented by psi B into V into dB we are going to get. Just I we took as an psi B into V, and psi that can also written as C divided by T. Here this can be written as, this can also written as Bi to Bf T divided by M Cb. Now d divided by dt can also written as C into B into V divided by T into dB. Now this can also written as minus of Bi to Bf integration of Bi to Bf T B into V divided by M into Cb d divided by dt of C divided by T into dB we are going to get. So if we simplify further, integration of Bi to Bf So T BV divided by M into CB is if we integrate this one, differentiate this one, we are going to get minus of C divided by T square into dV we are going to get. So minus into minus, that becomes a plus. CV divided by MCB into T, there is a term T and T square is there, and they gets cancelled, and remaining T in denominator we are going to observe minus in the range of integration of BI to BF B into dB. Now if we simplify, if we integrate this concept, CV divided by MCB into T, so if we integrate BF square minus of BI square divided by 2 we are going to get. So where magnetic field BF final magnetic field which is equal to 0, therefore TF minus of Ti is equal to minus of CV BI square divided by 2 times of MCB into T, and this is the final expression for low temperature, and this expression we derived by using adiabatic demagnetization. Adiabatic demagnetization in the sense, adiabatic in the sense there is change in a pressure, volume and temperature such that heat neither enters the system nor leaves from the system. Demagnetization in the sense the magnetic property is decreases in that given paramagnetic substance. Here we took a paramagnetic substance in this experimental arrangement, and it is surrounded by the liquid helium, and again it is surrounded by the liquid hydrogen, and this is placed in between north and south pole of a powerful electromagnet. What happens when a magnetic field is switched on? The temperature of this paramagnetic subsalt rises. So due to adiabatic process, the heat is conducted by the helium gas, and that is exchanged with the diffusion pump. Here they mention a diffusion pump, so that it is exchanged the diffusion pump. What happens if that if we pump out, the temperature becomes equal to that initial temperature decreases, and it falls to original temperature. Now when the magnetic field is switched off, what happens? The demagnetization takes place. While demagnetization takes place in the time, temperature further falls down, and that temperature is measured by the magnetic thermometers. Now by considering the Curie's law, psi t is equal to constant, that can be represented by psi 1 t1 is equal to psi 2 t2, psi 1 divided by psi 2, that can be written as t2 divided by t1. If we simplify, we are going to get this expression. We know that from first law of thermodynamics, dq is equal to this expression, and from second law of thermodynamics, dq is equal to tds. Therefore we are going to get this one. When the paramagnetic salt is placed in a magnetic field, the intensity of magnetization decreases by di. Therefore the work must be done on a salt solution, or salt, paramagnetic salt. Therefore that can be represented by b into di. Now the expression becomes TDS is equal to minus sign we are going to get because of a decrease in intensity of magnetization. Therefore the magnetization carried out at a constant temperature, therefore the change in a volume becomes 0. There is no change in a volume takes place. Therefore TDS is equal to du plus of b into di. Equation number 4 we are going to get. If the comparing equation 2 and equation 4, we are going to get, that is, so here the b minus b is replaced by p, and I is replaced by v. According to Maxwell's thermodynamic relations, so we are going to get at constant entropy. If we simplify, we are going to get an expression for low temperature, that is do T is equal to minus of T divided by M into Cv do I divided by do T of V into do B, equation number 7. And this expression that represents a fall in temperature of a specimen due to adiabatic demagnetization. If further expand an expression, by integrating we are going to get this expression, that is Tf minus of Ti is equal to minus of Cv Vi square divided by 2 times of M Cv into T. Here C represents a specific heat constant and the Cv that represents a specific heat at constant magnetic flux density. And this is about adiabatic demagnetization. And this completes your chapter, that is low temperature physics. Thank you.